Back, everyone. This is the third part of chapter 11. On some textbooks, it's actually the first part of chapter 12, depending on what version and what author and things like that. But we are doing analysis of variance, which is, and we're just going to tackle Way Anova for now. So we have a definition. We have one-way analysis of variance. And this is where the acronym ANOVA comes in, analysis of variance. Analysis, O is the of, the A is the variance. And one-way analysis of variance is a method testing the equality of three or more population means by analyzing the sample variances. So we're going to be analyzing sample variances, and which means we're going to be using an F table, and our null hypothesis, what we're testing is, are each of the means the same? For however many samples we want to have. And we only use ANOVA for three or more populations to test a claim. They all have the same mean, which is what we're looking at here. Now, the requirements of the populations have distributions that are approximately normal. Ideally, they are normally distributed. Populations have the same variances or standard deviations. The samples are simple random samples of quantitative data, and the samples are simple independent of each other. Now, here's our test statistic. And I'm not going to dive too deep into that. We're going to, because it gets so complicated with what we're doing, we're going to focus mostly on the technology that's behind this. So I want to jump into the first example. A certain statistics instructor participates in triathlons. The accompanying table lists times in minutes and seconds. We're going to have to fix that here in a second. He recorded while riding a bicycle for 5 laps through each mile of a 3-mile loop. Use a 0.05 significance level to test the claim that it takes the same time to ride each of the miles. Do the miles appear to have a hill? And what we're going to have to do with this data first is put it into lists, which I've already done. This is a little tricky because we have minutes and seconds. So let's scooch this up. So here's what I've done. When I put the data in, what I did for list 1 was I literally took 3 minutes is 180 seconds. So I did 180 plus 29. And 180 plus 29, you can see, is the 209. 180 plus 30, that's the 210. And so on. And so I put mile 1 into list 1. All seconds. Convert everything into seconds. And by the way, you can literally type it directly into here. So I can do 180 plus 29. And it puts it right into there for you. And you can do that with all of these. This is my list 2 and my list 3. So the null hypothesis is that the means are all the same. The alternative hypothesis is that at least one of the means is different. And even after we finish this analysis, we could go back and figure out which of the 3 means is the different one, but we're not even going to go that far. I'm just going to do sort of the basics here. Now, here's how this is going to work. What I'm going to do is, by the way, my alpha this is an F distribution. My alpha is 0.05. We have that here. Right, tilde, of course. And that's what we're going to be comparing our p-value to. So let me show you with the technology how we come up with a test statistic. So I'm going to quit out of this. I go to stats, tests, and I'm going to go up to the bottom. And here's ANOVA. With Anova, I'm just going to put the lists in. List 1, and again, let me remind you how to do that. Above the 1 is L1, so L1 and then comma, L2 and then comma, L3. It's going to give us our F. So our test statistic is F is about 28.3226. More importantly, the p-value, which is all we care about here, is, and I want to show you 2.85, but that's actually times 10 to the negative fifth. So what I'm going to do is I'm going to move that decimal over 4 places. 1, 2, 3, 4, 2, 8, 5, which is about 0. It's not worth splitting hairs over, which is clearly less than our alpha, which means we are going to reject the null hypothesis. All we're saying is that there is sufficient evidence to support the claim that at least one of 3 means is different. So he's faster or slower, at least a little bit, on one of these miles, is what there's, or is what the data has, we followed has shown. All right, let's do one more. The data found below amounts of greenhouse gas emissions from 3 types of vehicles. The measurements are in tons per year expressed as CO2 equivalents. Use a 0.05 significance level to test the claim that the number of different types of vehicle have the same mean amount of greenhouse gas emissions. Based on the result, what kind of vehicle or what type of vehicle appear to affect the amount of greenhouse gas emissions. So once again, our null hypothesis is that all 3 means are the same. Alternative hypothesis, at least one mean is different from the others. Once again, we are at 0.05. Level of significance. I didn't label the other one, but this is an F table, which again starts at 0. And to find that critical value, we need a complicated set of tables, which we don't need for right now. And so what I've done is, this one we don't have to do any converting when we go to, so I did 1, 2, and 3 for the first problem. 4, 5, and 6, you can see 7.1, 7.4, and so on, 7.9, 9.3. So I'm going to be using list 4, 5, and 6 to get my test statistic, and more importantly, my p-value. So with stat tests, I'm going to go up to the bottom of the list to Anova, and this is going to be, let me make sure you can see this. This is going to be L4, L5, L6. L4, comma, L5, comma, comma, L6, close. There we are. So our test statistic, F, is about 28.7 value. And you can see it's times 10 to the negative 7th. So let me, 1, 2, 3, 4, 5, 6, 4, 3. We'll just round it off, which is about 0, which is clearly way less than 0.05. Which brings us to our conclusion of, once again, we're going to reject the null hypothesis. So there is sufficient evidence to support the claim that different vehicles have at least one different. And that is as deep as I'm going to go with Way Anova. Thanks, everyone.